All right. So, somebody wants to get in. All right. So today we're going to talk about the Higgs mechanism. Higgs mechanism is a name for spontaneous symmetry breaking, meaning there's a theory with a local gauge symmetry, but the vacuum breaks it. That is, the vacuum is not invariant on the symmetry, and the symmetry actually takes one vacuum to another. In this case, the gauge fields that are broken, the gauge field for the symmetry that is broken become massive by the Higgs mechanism. And one says, we'll explain what that means, that the gauge fields eat a scalar degree of freedom along the symmetry direction in order to become massive. This works out with degrees of freedom, because in 4 dimensions, a massive vector has 3 degrees of freedom, while the massless one has 2. So has 1 degree of freedom more, and the scalar has 1 degree of freedom. So all right, we'll start with the simplest case. This is the case of an abelian gauge symmetry, U1. And for that reason, this is called the abelian Higgs system. Even though as an application, this is actually relevant for superconductivity, and not for particle physics, where the name Higgs mechanism originated. The Lagrangian for this system is then the kinetic term for the gauge field, -1/4 f mu squared. The kinetic term for the scalar, complex scalar, minus modulus squared of d mu phi, where d mu is del mu minus I/e a mu, minus the potential that depends on the modulus of phi. And the gauge invariance is phi of x going to a x-dependent phase, e to the I alpha of x, phi of x. And a mu of x goes to a mu of x plus 1 over e, d mu alpha of x. We will choose the most general. So, I mean, it's a choice in that it's the most general analytic gauge invariant renormalizable potential that has a symmetry breaking term. So the symmetry breaking is associated with the fact that there's a negative mass squared, so that the curvative near phi equal to 0 is negative. The field rolls down a potential. And then we add a quartic term. But more precisely, I mean, the reason I wrote it like this is that by adding a constant, which is irrelevant if you don't couple to gravity. If you couple to gravity, you can measure the constant as a mass. So if you add a constant, you can complete the square and write it as lambda over 2 modulus squared phi minus mu squared over lambda, everything squared. Now, why I say this is the most general analytic gauge invariant and not renormalizable potential? Well, we have seen that if the potential is renormalizable in 4 dimensions, it must have powers less or equal to 4. If it's analytic, it means it has to have positive powers. And so no poles. Gauge invariant means it depends on the modulus of phi, and then more precisely on the modulus square. So then the only possibilities are the second and fourth powers. And as I said, the fourth power needs to have a negative coefficient in order to break the symmetry, and the quartic term needs to have a positive coefficient in order to have stability both at -infinity and +infinity. Well, yeah, I mean at +infinity really, because we're talking about modulus squared. All right, so if the potential is like this, then we can see that the vacuum expectation value for phi is, so when you minimize the potential to obtain the vacuum, is when this modulus of phi equal to square root of phi squared of mu squared over lambda, which I define to, which I call phi 0. But then that means that the various vacua are actually this phi 0 times an arbitrary phase, e to the I theta 0. But by a gauge transformation, a global gauge transformation even, we can set the particular vacuum to the real vacuum, where the vev of phi is just phi 0. So yeah, so the gauge transformation removes the phase. This potential has been called usually the Mexican hat potential due to its shape, like a Mexican hat, in terms of phi in the complex plane. Come on. So in the Jesus. So in the complex plane, this being phi, this has this shape, okay, which is identified with a kind of Mexican hat or sombrero. The spontaneous symmetry breaking means that if one starts, so at time equal to 0, if you want, you should start on the top of the potential here at phi equal to 0. A small fluctuation will lead us into a random direction. So you can go either here or here. Remember, this is I'm representing a complex plane like this. So in any direction you can go, you will find. Sorry, this is not. Yeah, I mean V, and here this is the complex plane for phi. So starting at phi equal to 0, a small fluctuation from the top of this local mountain can give us into any valley, right? So then expanding around this particular vacuum, we can write, so phi of x is the vev, phi 0, plus a real part and an imaginary part. And the real part I choose to call phi 1 of x over square root 2, and the imaginary part phi 2 of x over square root 2. The reason for that is that if I expand the kinetic term, so the reason for this square root 2 is that if I expand this kinetic term around the phi 0, then the leading terms will be the standard kinetic terms for the real scalars, phi 1 and phi 2, 1/2 d mu phi 1 squared and 1/2 plus 1/2 d mu phi 2 squared. But then also the potential becomes, I write it as 1/2 times 2 mu squared phi 1 squared plus nothing at or quadratic order in phi 2, then plus third order in phi. So that means that phi 1 has mass square root 2m, square root 2 mu, and phi 2 is massless. And this phi 2 then is called the Goldstone boson associated with the symmetry breaking. So it's a massless field that corresponds to going into the direction of the vacua. It's a theorem that I'll prove next lecture, that for every symmetry that is spontaneously broken, there's an associated massless scalar called the Goldstone boson. Then expanding the kinetic term, as I said, the leading terms will be the canonical kinetic terms for the real scalars phi 1 and phi 2. But then I also have this mass term for the photon, E squared mu squared over lambda A mu squared. And then I'll also have a mixing between A mu and phi 2, the square root 2 E phi 0 times A mu d mu phi 2. So all of this is the quadratic part, and then there's higher order parts. So this term in the expansion, as I said, gives a mass term for the vector, for the photon, and the mass is, so I write this as 1/2 m squared. So the mass squared of A is 2 E squared, and then mu squared over lambda is phi 0. But then this term gives a mixing between the vector and phi 2. And what does mixing mean? Well, when you have a mixing, so at the quadratic term level, you have one field times another field. The way to do it is to diagonalize the kinetic term, so to remove this mixing. So we'll proceed to do that rather shortly. But before doing that, let's keep it and see that the resulting theory is still okay quantum mechanically. So we consider the Feynman diagram for this mixing as a kind of vertex, right? There's a vertex, quadratic vertex between the vector and the Goldstone boson, the scalar. And the Feynman rule then is I square root E phi 0. So it's minus I times this quantity. Then times derivative becomes minus I k mu. So all in all, this is square root 2 E phi 0 k mu, and square root 2 E phi 0 we've seen is MA. So this is MA k mu. Considering now the modification to the photon propagator. So I write the full photon propagator in this way. So there's so this is the full quantum propagator, and it contains the for the for the 1pi part, I write the original one in the Lagrangian, which in the Lagrangian is just the mass term. So 1pi term, 1pi part is just the mass term, which is MA with so there's a vector and the MA, and then another vector. So this is thought of as a, since it's a 1pi diagram, it's thought of as a kind of vertex, even though it's quadratic, and even though more it is a mass term. But then to this I must add other contributions due to these vertices. So these vertices mix the field. So what happens is, if I have to have vertex on the left and on the right, I have to have this mixing, then propagator for the scalar, then another mixing. So when I write this Feynman diagram, I write, so the mass term is thought of, as I said, as a vertex. So then it is minus I times MA squared times G mu nu, because this couples an A mu with an A nu. And then plus plus the mixing, MA k mu, times the propagator for the complex scalar, minus I over k squared. The scalar, the Goldstone boson, is massless, so it's minus I over k squared, times the mixing, but now it's in the other direction. So now it has a minus sign. And then I combine these two terms, and I see that what I obtain is minus I MA squared times G mu nu minus k nu over k squared, which is a transverse 1pi term, as it should be in a gauge invariant theory. So this shows that even though I expanded around a broken symmetry vacuum, the underlying theory is still gauge invariant. So I still have transverse 1pi quantities. Okay. All right. Continuing with this Abelian case to understand what's happening in more detail, let's consider the unitary or physical gauge. So that's a unitary or physical gauge is when we use the local gauge transformation alpha of x to get rid of one scalar degree of freedom, and specifically in the U1 symmetry direction. That is to say, the Goldstone boson. So I put phi2 equal to 0. So if phi is real. So looking here, so phi 0 is real, then phi 1 is a small perturbation in the real direction. So if I look in here, let's say this is the real direction. So so this would be phi 1, and then in the complex direction like this would be phi 2. That's transverse to phi 0. So from the point of view of, so considering that these are just small fluctuations, this corresponds to going around, going into this phase. So phi 2 corresponds to theta 0 in here, to rotating the field phi. In other words, corresponds to the U1 symmetry direction. Okay. So that means that really we can get rid of phi 2, put phi 2 equal to 0 using the local gauge transformation alpha of x. Phi 2 is a function of x also, but alpha is function of x, so I can do this. Then in the Lagrangian, well, the kinetic term for the gauge field remains unchanged, minus 1/4 f mu squared. Then right. Okay, so I now have written this in terms of, as I put phi 2 equal to 0, but then I went back to the notation where I have a real phi instead of just phi 1 and phi 2. So I just called phi 0 plus phi 1 over square root 2 phi, right? Since phi 2 equal to 0, this is still phi. So the kinetic term then is minus d mu phi squared plus minus e squared phi squared a mu squared minus u of phi. So then we note that indeed what we said happens, that the Higgs mechanism is such that the gauge boson is quote-unquote eating the Goldstone boson. So we put the Goldstone boson phi 2 equal to 0, and then the gauge boson gets a mass because this e squared phi squared acts as a mass term for the gauge boson. We can now, so in this representation, I chose phi 2 equal to 0 in order to compare with the previous analysis. But it is better to see this in the parameterization with the modulus and the phase. So if I write the complex phi as a modulus now, not a real phi, but rather a modulus, which is real and positive, times e to the I theta, then the covariant derivative of the scalar becomes, well, when I take the derivative, I always have e to the I theta in front, then times d mu absolute modulus phi squared plus I d mu theta modulus phi minus I e a mu modulus phi. So choosing the real vacuum, modulus phi is phi 0 and theta 0 is 0, and expanding around it like before, but well, so writing rather modulus phi is equal to phi 0 squared, or mu squared over lambda, plus delta modulus phi over square root 2, right? Then the theta degree of freedom is removed by the redefinition. You see, I have here d I modulus phi times d mu theta minus a mu. So if I redefine, instead of a mu, I write so I write a mu equal to a mu prime plus 1 over a d mu theta. This leaves the field strength invariant. This is just a gauge transformation, really. So then f prime mu nu is equal to f mu nu, but then theta has been eaten. So the degree of freedom, the Goldstone boson, the degree of freedom in the symmetry direction, theta, has been eaten by a mu in this way. So that's what eating. That's what it means that the vector eats the Goldstone boson. There's a redefinition after which the Goldstone boson disappears from the action. Because now modulus squared of d mu phi is modulus d mu of modulus phi squared plus e squared a prime mu modulus phi squared. So now there's no more theta, and modulus phi squared acts as a mass term for a prime mu. And so I can rewrite the Lagrangian as approximately minus 1/4 f prime mu squared minus the kinetic time for delta modulus phi minus this mass term for a prime mu. Now, I want to stress, to make an important historical note, that this is called the Higgs mechanism. And Higgs certainly did an important contribution. He wrote several papers and made things clearer to most people. But however, the so-called Higgs mechanism was discovered jointly. There were several papers, not only by Higgs, but also Kibble, Guralnik, and Hagen. And Kibble by himself, I think, Guralnik and Hagen, and then Englert and Braut. I think it was like this. Well, I knew Jerry Guralnik before he died, and then he said that he was a postdoc at the time, and he wanted to publish earlier, but he was discouraged by some more senior physicists who thought this was junk, not interesting. But anyway, so it was something that was known at the time. Moreover, the Higgs mechanism itself, so I said Higgs mechanism, but the Higgs mechanism itself refers more precisely to the non-Abelian gauge theory, to what we'll describe next, and to the application to particle physics. When you think of, like we said here, that these are particles and there's a quantum theory for it and so on. However, this fact of that there's a symmetry breaking and the vector boson eats the Goldstone boson, this was discovered before in the context of superconductivity. And there was a version of this Abelian Higgs mechanism that we described that explains the so-called Meissner effect, which is the fact that the magnetic field only penetrates a small distance of the order of 1 over mass scale inside the superconductor. So the magnetic field is expelled from the superconductor. And the reason for that is that you see the photon inside. So inside the superconductor, you have a symmetry breaking, and the photon becomes massive, the real photon, the electromagnetic photon. And therefore, it penetrates only a distance of order 1 over m photon inside the superconductor. All right. Well, so one thing you might ask now is, what about the gauge symmetry? So you have a theory that has a gauge symmetry, a local symmetry, and then that symmetry is broken in the vacuum. So what happened to the gauge symmetry? So before the Higgsing, the symmetry breaking, the gauge invariance was the variation of A mu is d mu alpha, and the variation of phi, that is absolute value phi e to the I theta plus I e alpha, minus absolute value phi e to the I theta, which means delta theta is E alpha. Then expanding around the vacuum, just expanding around the vacuum, does nothing to the symmetry. The symmetry is still there. It's very important to realize this. You just did an expansion, so because of the expansion, if you keep only some terms, it might seem that the symmetry is not there, but the symmetry is there. However, what happens is that the redefinition, the eating of the Goldstone boson by the vector, that redefinition, A mu going to A mu being rewritten as A mu prime plus 1 over E d mu theta, that redefinition does something to the symmetry. Because after the redefinition, delta A prime mu is delta A mu minus 1 over E delta d mu theta. This is equal to 0. Right? If you just substitute this, you see this is 0. And delta absolute value of phi, it was 0 anyway. So after the redefinition, there is no more gauge symmetry. But before the redefinition, even when expanding around the vacuum, you still have a symmetry, well, if you keep all the terms in the expansion. Okay. Another point to note is that while it's also common to call phi the Higgs boson, actually the actual scale, the real part of the real scalar absolute value phi, or in other way, its variation phi 1, has a mass, and therefore this object with a mass deserves the name the Higgs boson, since it's the boson associated with the particle that we observe in experiments. But the Goldstone boson, we don't observe because the Goldstone boson is eaten by the vector field, right? So that's not something we observe. So it's an important distinction to note. So even though theoretically you might call phi the Higgs, in terms of phenomenology or experiments, what is the Higgs boson is just the massive fluctuation, the one transverse to the Goldstone boson. All right. We also note that in the scalar kinetic term expansion, we have this term, E squared square root 2 phi 1 phi 0 a mu, which also after redefinition becomes, so after redefinition becomes the same thing, but with a prime and then plus higher order terms. That comes from this redefinition. Sorry, higher order in the fields. Right? This one means that, so in terms of fields, what are fields here are these three, right? These are constants. So there's phi 1, which is the Higgs boson, Higgs particle, and then A prime, which is the massive vector that we observe. It's a massive particle that we observe. So this is a vertex for two gluons to join and emit a Higgs boson. And the vertex is square root 2 E squared phi 0 delta mu. All right, now let's go over to the non-abelian case. Let's consider a non-abelian gauge group G with the gauge transformation written as now a matrix product, so phi I going to a matrix with indices ij times phi j. And that matrix is exponentially written, and but with two conventions. I wrote it here. One, the convention with e to the minus I alpha a little ta, or e to the plus I alpha a capital Ta. So with either Hermitian or anti-Hermitian generators. And then the covariant derivative is written as either in d mu minus I g a mu a little ta, or d mu plus g a mu a capital Ta. And then the kinetic term for the scalar is 1/2 times this covariant derivative square, which gives 1/2 d mu phi I squared plus this third order terms in the fields, g a mu a d mu phi I ta ij phi j, plus this quartic ordered quartic term in the fields, g squared over 2 a mu a b mu ta phi with index I tb phi with index I. And now let's consider the vacuum expectation value. So I haven't told you what the field is, what the potential is, but let's assume that it's vacuum expectation value. So there's a potential that is invariant also under this gauge group, and let's assume that it breaks the symmetry and it has a vacuum expectation value, which is phi 0 with index I. Then from the kinetic term for the scalars, we obtain this mass term minus 1/2 m squared, but now it depends on, which type of gluon do we have. So it's m squared AB, it's a matrix connecting gluons A mu A with A mu B. Then this mass matrix m squared AB is G squared TA phi 0 I, TB phi 0 I. And the diagonal elements are for A equal to B. So G squared TA phi 0, everything squared, which is positive or 0. That means that the vectors have mass squared that is positive or 0. So that's different than in the Abelian case. In the Abelian case, we had only one vector, and that became massive. But in this case, there are several vectors corresponding, several gluons corresponding to the various values for A. And in general, we can have some of them to be 0 and some of them to be non-zero. So the ones that are 0 corresponds to unbroken gauge symmetry. All right, so let's understand this better theoretically. So we have a gauge symmetry for a gauge group G that is broken spontaneously by this vacuum phi 0 to a subgroup H that leaves the vacuum invariant. So phi 0 is invariant under the action of the subgroup H. Now, comparing the Abelian case, the vacuum was just a point. So there was no unbroken gauge group. There was nothing to that point. There was no way to act on it to leave it invariant. Now, the generators in the coset G over H, that means the generators in G that are not in H, they take us from one vacuum, which is invariant under H, to another one. But these all vacua are all equivalent, like we said before in the Abelian case, the action of the symmetry on the vacua phi 0 e to the I theta was trivial in the sense that all the vacua were equivalent, and yeah, we could rotate one to another. So these unbroken generators in the coset give rise to the Goldstone bosons. These are the massless vectors. Now, in the case of D1, this was the whole vector. So these unbroken massless generators then corresponds to, so if m squared A is 0, then TA phi 0 is 0. So this condition defines the group H. We have to then do the same redefinition or eating of the, so this redefinition or eating of the Goldstone boson by the vector. So we write A prime mu A is A mu A minus D mu phi I times TA phi 0 I. It means that the broken vectors with non-zero TA phi 0 eat the Goldstone bosons and become massive. Okay. And again, the same story as before. If we don't do this redefinition, we note that there is a mixing vertex between a mu a and d mu phi I, which is of this type G times a mu a d mu phi I times ta phi 0 I, this thing. But nevertheless, the theory is transversal, which means it's gauge invariant. So it's consistent at the quantum level by exactly the same picture as before. So the same picture we had here. So we write the 1pi vertex, quote unquote, for having one vector on the on one side and one vector of the other side, and then write the non-zero, the trivial part, which is just the mass term, and then plus another one, which is the mixing vertex times the propagator for the scalar, for the Gaussian boson, and then another mixing vertex. So doing that, I write minus I m squared AB now, G mu. This is the trivial part. And then the mixing part is the mixing vertex G K mu Ta phi 0 I, the phi 0 J, okay, times the propagator for the Gaussian boson. The propagator is still minus I over k squared. Well, I guess probably have been delta ij in here. Anyway, it doesn't matter. The propagator is massless and it contracts these indices. And then times the other mixing vertex minus g k mu tb phi 0 j. And then we put these two together. So the minus was because the derivative acts on the left-hand side instead of the right-hand side. So in Fourier space, that gives a extra minus sign. And then you put these two together, you get minus I m squared AB times G mu nu minus K nu over K squared. So this 1pi is, as expected, transverse. So we have gauge symmetry in the theory. It's at the quantum level. Yeah. In other words, you think of this as a vacuum polarization, pi mu nu, which, as we saw, because of gauge symmetry, should be written as pi times this coefficient, d mu nu minus k nu over k squared. Next, let's apply to the simplest non-Abelian case, SU2, which is also happens to be very relevant because it's very close to the electroweak theory that we'll study next, which is SU2 cross U1. All right, so it's a theory with a phi that is in the fundamental representation, that is in a doublet one of SU2. So the covariant derivative on phi is, as before, del mu minus ig a mu a times the generators, and the generators are the Pauli matrices over 2, sigma a over 2, times phi. And the potential is written now as a trivial generalization of the U1 potential of the Mexican hat one. Is lambda, well, lambda instead of lambda over 2 because now we have a doublet, but yeah, it's just a normalization. So lambda times phi dagger phi It's not phi star anymore because now it's a matrix. It's phi dagger phi minus mu squared over lambda, everything squared. And we choose the vacuum as before to be real. But moreover, now we can make not just an U1 rotation, but an SU2 global rotation. So making an SU2 global rotation on the vacuum, I can put it into the form where the top value in the doublet is 0 and the bottom value is non-zero, but moreover real. So, and I choose to write it as V over square root 2. Then the scalar kinetic term becomes the modulus squared of d mu phi in this vacuum. Del mu of phi is 0. This is constant. And then I have only the quadratic part in the vectors. So I have g squared times tau a times phi squared. So I have tau a e mu a times phi, which is 0 v over square root 2. Then times another tau b a b mu phi, which is again 0 v over square root 2. So all in all, 1/2, and with a g also in front. So all in all, 1/2 g squared, 0 v tau a tau b, 0 v a mu a mu b. Since we have a symmetry in this indices a and b because of the contraction over mu, we can replace tau a tau b with the anticommutator over 2. So tau a tau b anticommutator over 2 is, of course, delta ab over 4, because tau a is sigma over 2. And the anticommutator of, so sigma a times, anticommutator of sigma a sigma b is 2 delta ab. And finally, then we obtain, and so we get rid of this, and then we have only the contraction of this, which gives just v squared. So all in all, we get this mass term, which is g squared v squared over 8, a mu a mu a. So that means that the vector mass is gv over 2. Okay, let's finally go to the standard model. Standard model Higgs. That's the electroweak SU2 cross U1. So in the electroweak theory, the covariant derivative would be del mu minus, for the SU2, I have minus g a mu a tau a as before. And then for the U1, I have minus I g prime times b mu over 2. So this is a normalization, but the normalization is supposed to mean that there's a hypercharge y for the field phi that is 1/2, right? So the hypercharge of the field of the Higgs is 1/2, and b mu is the gauge field associated with U1. Then this sum here, a mu a, sorry, G A mu A tau A plus G prime over 2 B mu is written as, remembering tau A is sigma A over 2, so I get a common 1/2. And then on here I have G, on the diagonal I have G sigma 3 plus G prime B mu. So G A mu 3 plus G prime B mu here, and minus G A mu 3 plus G prime B mu. And then on the second diagonal, I have G A mu A1 minus I A mu 2, and G A mu 1 plus I A mu 2. And the potential is written now in a similar way as in here, just with different normalizations, different definitions. So I write it as lambda over 4 phi dagger phi minus v squared over 2 squared. But then, so yeah, mu squared over 2 was by definition v squared. Sorry, by definition was before, by definition v squared. Yeah, in both cases, by definition v squared over 2. So then the vev of phi can be put by a global SU2 transformation to this form 1 over square root 2 0 v as before. So where I choose to the gauge transformation such that the top value is 0 and the bottom value is real, and written as v over square root 2. Then the mass term is, I mean, in the same way as before, I have as v squared over 2 from the phi squared, and then I just keep the matrix part, which is 0, 1 here and 0, 1. I have the common 1/2 from the derivative, which is squared now, so this gives minus v squared over 8. And then I have this matrix modulus squared. So when you do the calculation, you obtain that is minus v squared over 2 times g squared a mu 1 squared plus g squared a mu 2 squared plus minus g a mu 3 plus g prime b mu squared. So we see now that in order to make a connection with the physical experimental case, I define the fields W plus minus to be a combination of these two terms, the combination corresponding to sigma plus and sigma minus. The Pauli matrix is sigma plus, sigma minus. So a mu 1 plus I plus minus I a mu 2 over square root 2. And then the other combination that appears in here that has a mass term, I'll call Z. That's the particle Z0. So Z0 mu is this combination, G a mu 3 minus G prime B mu, but normalized to be with 1 over square root G squared plus G prime squared. And then the unbroken one will be the one with plus in here. And this will be a mu. That will be the unbroken electromagnetism that is left over from the symmetry breaking of the electroweak SU2 cross U1. So then you just substitute these redefinitions in here. You see, well, this redefinition we know just changes these sums of squared to a product of the two. So it's minus v squared over 4 g squared w plus mu w minus mu. And then here I just have this z, the mass term for z0, so z0 mu squared time the mass term is now v squared over 8 times this normalization, g squared plus g prime squared. So we see then that the w plus and minus have the mass gv over 2. W plus and minus are massive bosons that are observed in particle experiments and at the electroweak scale. And Z0 is also a massive boson, also at the electroweak scale. But instead of GV over 2 is, so instead of G, I have this square root G squared plus G prime squared, V over 2. And then, as I said, A mu is a massless vector corresponding to the unbroken electromagnetism. So comparing with our general theory before, we see that the unbroken photon, it's unbroken because we have TA phi 0 equal to 0 for them, and for the other ones, TA phi 0 is non-zero. We can introduce the so-called weak mixing angle or Weinberg angle, theta W, for either weak or for Weinberg, as defined by this the ratios. So cos theta W is G over square root G squared plus G prime squared, and then sin theta is of course G prime over square root G squared plus G prime squared, which makes it obvious that this is really a rotation. So between Z0 and A mu, so Z0 and the mu is really a rotation of the third, so the component along tau 3 of the SU2, so A mu 3, and the hypercharged gauge field B mu. So a rotation with the rotation matrix cos theta W minus sin theta W cos theta W. So this is just an orthogonal rotation, right? The same way as this was also a rotation. We also do the redefinitions, T plus minus being T1 plus minus I T2, which is equal to sigma plus minus, the Pauli matrices sigma plus minus that corresponding to creation and annihilation. And I redefine, I define the electromagnetic coupling E in terms of the SU2 coupling G and the U1 hypercharge coupling G prime as E equal to G prime over square root G squared plus G prime squared, and the corresponding electromagnetic charge Q as T3 plus Y. So the T3 being the generator along the direction in SU2 that is rotated, and Y being the hypercharge, the U1. Okay, then the covariant derivative which was del mu minus ig a mu a ta minus ig prime y b mu, is now rewritten as del mu minus ig over square root 2 w mu plus t plus w mu minus t minus for the w's. Then for the z, I have minus I over square root g squared plus g prime squared z mu g squared t3 minus g prime squared y. So yeah. Yeah, okay. I guess it's obvious, as I said, from the rotation, the fact that this is a rotation. Minus I g prime over square g squared plus g prime squared a mu t3 plus y. But then we also notice that this combination g squared t3 minus g prime squared y can be rewritten as g squared plus g prime squared t3. So I isolate q, and then I have another contribution to t3. Then I have minus g prime squared q. And also I note that this E is g times sin theta. So g prime over this. So this is sin theta w. So E is g times sin theta. So I write then in here, so I have in the z, for the z term, I have g times then g over this square root is cos theta w. Okay, this is probably not right here. This should be g times cos theta w. Then, well, no, sorry, yeah. Yeah, so q is t3 plus y, right? So then I write y as q minus t3. So then I have here g squared plus g prime squared over square root. So this is square root of g squared plus g prime squared, which is g over cos theta w in here. And then I'm left here with g prime squared times q, g prime squared over the square root times q, which is yeah, for some reason then it's sine squared theta w over cos theta w. I don't see it. Let's see. Sin squared theta w is g prime squared over this, g squared plus g prime squared over cos theta w, which means is g prime squared over g squared but then everything times square root. Oh, well, it's probably like this. I don't see it right now. And then in the A mu case, I have this combination that was E, GG prime over G squared plus G prime squared. And then this was Q. So minus I E A mu Q, which is what I expect for electromagnetism. Right? E is the coupling and Q is the charge. We also obtained then a relation between the masses and theta W. So MW MZ versus MZ. Right? So the ratio MW over MZ is G over square root G squared plus G prime squared, which is cos theta W. So this is this relation. Then, moreover, in unitary gauge, I have only unitary gauge. It means I use the global AC2. I use the local AC2 to fix the field to be only one one real field. So I still keep equal to 0 the top value, and I still keep real the bottom value. So it's V plus H of X over square root 2. And then this H is the actual Higgs boson. That means the field associated with the Higgs particle. Then expanding the potential V of phi in terms of H, I obtain lambda V squared over 4 times H squared plus lambda V over 4 H cubed plus lambda over 16 H4. So from this we see in particular that the mass of the Higgs is, so mh squared is lambda V squared over 2. And then there's this 3 Higgs coupling and the 4 Higgs coupling. So this is a vertex for 3 Higgses. And this is a vertex for 4 Higgses. And then finally the electroweak bosonic Lagrangian, so without fermions, just the gauge field and the Higgs, quote unquote, is the kinetic term for the bosons of -1/4 F mu A squared -1/4 B mu squared. The kinetic term for the scalar -1/2 modulus squared of d mu phi minus the potential V of phi. And then I left it as an exercise for you to check that this is rewritten as, well, no surprise that the kinetic terms become the kinetic terms. The kinetic terms for the gauge boson becomes the kinetic terms for the other gauge boson. So the electromagnetic -1/4 F mu squared. The massive field is -1/4 Z mu squared, and then minus d bar dagger mu W minus mu. So this is the massive W minus times d bar mu. Sorry. no, not d bar, sorry, the tilde dagger mu here, and then here is the tilde mu w plus nu, where d tilde is del nu minus I e a mu plus cos theta w z mu. So this also contains a coupling to the z of the w particle to the z. And yeah, here is the other one with wait, no, I've right. Yeah, okay. So I write it with d mu covariant derivative, and then there's a minus and a plus because I have here I have mu nu, here I have mu mu. So this contains, so if I ignore these covariant derivatives, if I have just del mu, then this would give the kinetic terms for the field W mu plus and W mu minus. Right? It's like expanding the electromagnetic F mu squared over 4. I'll get minus 1/2 d mu a nu d mu a nu plus 1/2 d mu a nu d nu a mu, and that's what happens here. Then I get this mass term for W plus W minus. Sorry, this is the mass term for W plus W minus with mw squared times 1 plus m over v squared. And then mass for z with mz squared over 2 z mu. Then there's this coupling for W plus W minus with electromagnetism and z, and the 4-point coupling for the W's, W plus, W minus, W minus. And finally, the term for the Higgs, so the kinetic term, minus 1/2 d mu h squared, the mass term, minus m h squared over 2 h squared, and then these cubic and quartic terms in h. All right, but I left the proof of this for you as an exercise, given all of these various terms that we've written here. All right, so this is the electroweak Lagrangian, and this is everything I wanted to tell you today. Do you have any questions? Can you check that you can still hear me? Okay, so that means that you don't have any more questions. All right, so I'll see you on Tuesday when I'll start talking about renormalization of these spontaneously broken gauge theories. All right, that's all. Bye.